everyone. My name is Matt. I'm a software engineer at Scale. And today we're going to be talking about something I call Spo-tfidf-y, which is a fun that you don't get now, you'll get it later, it'll be hilarious. And yeah, basically we're going to learn about some kind of basic, you can call it ML if you stretch it, techniques that you can use to kind of categorize things you don't think you could usually categorize, right? So like a song, for instance, right? How do you compare songs to other songs, right? That's kind of hard to do, but we know how to compare vectors to other vectors. So hopefully by the end of this, y'all will be experts at comparing songs. So songs are kind of just lots of words. So we'll start by talking about how to compare words instead. And yeah, basically, imagine we have like two sentences, right? We kind of want to be able to define, again, like quantitatively, what a sentence represents. And so we're going to kind of go through some simple methods to do this with these two dummy sentences right here. So the first sentence, my dog is named Fido. Fido likes to bark and runs fast. And the second sentence is my cat is named Furu. Furu likes to purr and is fluffy. And so we have a third sentence out here, which is my puppy is cute and can bark loudly. So as humans, if I were to ask y'all what it's most, like which of the previous two sentences it's most similar to, y'all would probably say number one, just because we kind of have this like semantic information that puppies are like similar to dogs, right? And also we say bark. Yeah, so that's like really easy because our brains are like really complicated, right? But at a hackathon, we cannot make things that complicated. We got to make things like a little less complicated and take some shortcuts. So today we're going to learn about some of those shortcuts. So the first shortcut, which is like a super big shortcut, is we create vectors from these sentences where we kind of just count the number of occurrences of each word in the sentence. This is called the bag of words approach, hence the cute little emojis at the end. And so here's kind of an example of what this might look like, right? So to start, we need to get kind of the set of all distinct words from all of these sentences, or we might call them documents as well. And so we see that as rows on the left side. And so, my dog is named Fido, likes to bark and fast, runs, cat, fur, et cetera, right? And then in the columns, the number, I guess in a given row column, represents how many times that word occurs in a certain document, right? So this is like a very straightforward approach, but being as straightforward as it is, it definitely has some limitations as well, which we'll see in a few. But I guess to start, any questions kind of about how we're able to generate these word vectors, again, by counting the words in a given document? Any questions so far? Also, feel free to raise hands and ask questions as you have anything. Cool. So all good so far. Let's try to compare our first sentence to our third sentence, right? And so basically what we're doing here is, I'm doing a little bit of a shortcut because if there's no common word, right, it doesn't make sense to compare them. I guess for more context, we're going to take the dot product of these vectors to compare them. So if, one entry of your first sentence, or the first set of words, doesn't exist, right, that's a 0, and the dot product of the other thing will be 0. So we're only tracking things where the dot product is not 0, the value is not 0 in the first doc or the third doc, because that's what we're comparing. So those 4 words we get are my, is, bark, and. And each of those only occurs once in each of the respective documents. So with that in mind, we kind of just get 1 times 1 plus 1 times 1 plus 1 times 1 plus 1 times 1. And it's kind of hard to see the color coding, but the math's kind of color coded towards the given word that we see, right? And that gives us a dot product of 4. And so in this case, a bigger dot product kind of means that the words, maybe dot product's not the best, these are not like unit vectors, but bigger dot product will basically mean these words are more similar than a given dot product on a different sentence. And so now we're going to try to look at the dot product of the cat sentence. And hopefully, that will be less, and that will tell us that our intuition is correct, and that the dog sentence is more similar to the puppy sentence than the cat sentence is to the puppy sentence. So let's look at the math here. And lo and behold, this simple method, which I aggressively foreshadowed, is not quite enough to give us like a meaningful difference here, right? So in this case, looking through the example, we see my is present in both documents again, and that has a value of 1, right? And so that gives us the first little one. Is present twice in document 2, and so that kind of inflates the value of is, which gives us this big fat 2 right here, and then and is present in both, which gives us this 1. And so it's kind of tragic, right, because now our computer doesn't actually know if the dog sentence or the cat sentence is more similar to the puppy sentence, right? And yeah, I guess with that, does anyone have like an intuition as to what caused this big failure in our system? Any ideas of the culprit here? Yes, what's up?
You don't account for the frequency of words.
Exactly.
Words.
Yeah, right. So is, that's one part, right? And the other part is that like, if we do, yeah, if you're saying like across the documents, right? Yeah, right. So is present in every document. Right, and so like you said, because is present everywhere, it's kind of like a meaningless word, right? If we put the same word everywhere, we kind of devalue it. It's like word inflation almost, right? Whereas puppy is like, in this case, a very unique word. It only occurs once, right? Bark is pretty unique as well, right? It occurs twice. And yeah, things like is and my and, they're kind of like filler words, right? Like putting the word the in the sentence, right? That doesn't add that much semantically. So we're going to learn how to kind of ignore that in a tasteful, mathematical way up next. So yeah, we covered this. They're the same, and it is leading to the inflated score. So this was kind of part of the pun in the middle, or at the start of the presentation, is the TF-IDF y'all saw, and that stands for term frequency, comma, inverse document frequency, which are two numbers we're going to compute. And at a high level, what this does is it lets us kind of weight commonplace words less than more distinct words. And so to start, term frequency, which is the first kind of part of this phrase, very straightforward. It's just how often a word occurs in a document compared to the rest of the words in the same document, right? So in the sentence, hack MIT is lit, right? There's 3 words in there, and so that's kind of like the denominator, right? And so to look at a given word like hack MIT, that's term frequency would be 1/3, right? And he said hello world, hello world, hello world. Both hello and world, they occur 3 times, and we have 6 total words, so they have a term frequency of 1/2. And so these are kind of computed at a per sentence or like per document basis, which is a little different than inverse document frequency we'll cover next. Any questions about term frequency so far? Cool. Yeah, so inverse document frequency sounds like kind of complicated, but it's also not that complicated. So if we have n documents, right, or think of like the 3 sentences we had before, right, and a term appears in some like subset of them, the inverse document frequency is just the log of n, which is again our total set of documents, over k, the amount of times it appears. And what's really cool about this is it kind of weights words that appear in a lot of documents a lot less, right? And in the most egregious case, if you have a word that appears in every document, so n, right, we get log of n over n, which is log of 1, which is 0, and so we kind of just totally ignore that word, which is really cool, and that kind of gets rid of like dummy or like kind of filler words from there. So yeah, in another word, it represents how boring the word is. Yeah. Any questions about inverse document frequency so far? Cool. Yeah, and TF-IDF, if you understand those 2 parts, the total TF-IDF is very easy. It's just the product of both of those. Yeah, easy peasy. And now we'll look at a big example. It's not as complicated as it looks. I would say just that the numbers are kind of long. So here, we can see. Let's just look at a few like rows in particular, right? So Fido, the term frequency of Fido in document 1 is 2, right? And there's 12 words total, so that gives us a 2/12 for the term frequency. And the inverse document frequency, since Fido only appears in one of the 3 documents, is going to be log of 3/1, right? And you can see this for kind of the rest of the rows. Nothing too crazy here, just quick math, and yeah. This basically gives us like a big matrix that we can leverage going forward. And so now we're going to kind of recompute using our brand new formula the closest sentences. So we're going to start with our dog example, right? And our words here are my, is, bark, and. Which is really nice for the math we're going to do. My, is, and all have inverse document frequencies of 0, which means like multiplied by the term frequency turns into a 0 as well. So if you take all these dot products, basically at the end of the day, all you're doing is kind of dot producting the bark you see. And that gives us a score of 0.004 to so on. And so let's keep that in our noggins as we look at the next example, which is cat. And this is even prettier than the last one because all of these kind of filler words now turn into zeros thanks to the inverse document frequency. And now we get a big fat 0 for our similarity between the cat sentence and the puppy sentence. So that tells us quantitatively with pure computer science and mathematics that the dog sentence is a lot more similar to the puppy sentence than the cat sentence is similar to the puppy sentence. Yeah, so there we go. 0.004 is bigger than 0, and document 1 wins. Any questions about that, or if not, we will keep on stuffing. Cool. So here's kind of a cool extension of TF-IDF, right? Or not even an extension, it's kind of just built into it. Previously, we were looking at the matrix kind of from a column perspective, right? Because we were comparing documents. Oh, what's it?
We have 2 questions.
Oh, yeah.
So one of them is, why do you take the log in the IDF? What significance does that have?
That's like a good question. I think like you can kind of do whatever you want, right? But it's kind of like a free thing you can do, and it's also just really nice because it turns kind of the 1/1 into 0. So I don't have like an exact answer there, but yeah, I think it just tapers off well as well, versus just like having like a linear thing, which would just make the magnitude a lot more. Yeah, but I don't have an exact answer. That's kind of the intuition there. Was there another one?
Oh yeah, the other one was, is TF-IDF similar to the kind of work Scale does?
So I'm going to touch on that a little bit more at the end. Yeah, there'll be some shameless plugging, don't you worry. But yeah, we'll talk about that afterwards. But yeah, good questions. Cool. Okay, back to this, right? So we were looking at the columns here, right? And we were kind of comparing column-wise the vectors to compute like document similarity, which is cool, right? If you put in like 2 documents, you want to figure out how similar they are. That's pretty cool. But arguably, what's even cooler is computing how similar words are, right? And you can kind of use that to generate like vectors of words, right? And so in this case, we can check, is bark closer to dog or to cat, right? And here we're looking kind of at these the word vectors now of dog, cat, and bark, and dot producting kind of on the transpose of that instead. And here we can see because dog appears in the first document and bark appears in the first and the third document, right? Whereas cat only appears in the second document. The dot product of those two gives us quantitative proof, again, that dog is more similar to bark than cat is similar to bark. So this is like pretty cool, right? Because we started with words, which, if you just have words, there's, again, no innate way of comparing them. And now with this like really straightforward algorithm, we've built out a way of like quantitatively being able to compare both like sentences and words semantically, which is really neat. But if you think about this, TF-IDF is kind of just like an arbitrary like set of things, right? And there's no rule that this set of things has to be words, right? You can make it whatever you want. And instead, we can just use playlists as the documents, and words, instead of words, we can use songs. And so this is like really cool because now we basically unlocked a way of like making our own Spotify blend. I don't know if y'all are have played with that yet. That's pretty cool. But now we can kind of just compare songs and make song vectors and do really cool things with songs. And we'll talk more. There's obviously there's a lot more things that kind of just fit this high level that can be represented with sets. But we're going to talk about songs first. One interesting thing about playlists versus sentences or documents is that playlists usually don't have a song repeated, whereas sentences do. So that like kind of muddles with their term frequency definition, but the term frequency is like still kind of important because we have this denominator of like the total magnitude, right? So if you have a playlist with like 3 songs, right, every song will only have like a numerator of 1, but the denominator will still be like 1/3 versus a playlist with like 100 songs. Now your denominator is going to be 1/100, and so you still have like a little bit of information encoded with your term frequency, but it's like a little bit different. So with that in mind, I have like a little Jupyter notebook set up, and then also if y'all want to go, I'll put this in the Zoom chat as well. I like made like a little baby repo that people can kind of follow along with. But again, I'll be sharing the Jupyter notebook as I go through it, and we'll kind of talk about some ways to kind of play with the data Spotify gives us. Spotify has a really cool API as well that allows us to do some really neat stuff too. So with that in mind, we're just going to start by looking at like a kind of simple implementation of like tf-idf just for like an arbitrary document. My Python's kind of crusty, so forgive any weird things you see in there. But we're going to start with a few things. For starters, usually when you're working with any kind of like textual data, sanitization is pretty useful and important. So we're just going to define like a really quick string sanitization method right here, and import a bunch of random stuff we need. NumPy is just good for working with matrices. String has some like random enums that we can use for sanitization. And then we're just going to go. That is yes, that is good. A good call for sure. I think that is a lot better. Cool. And now we're just going to make this simple like tf-idf formula. And this is pretty straightforward. It just will take in a list of strings, right? And it's going to output basically a matrix like we saw earlier, as well as a description of kind of the given word that exists in a given row of the matrix, because otherwise we lose our words. So to start, right, we basically will just sanitize our input and create this list of kind of documents with words in them, right? It's going to be like a 2D array here. And then the next thing we have to do is take all of the unique words, as I mentioned earlier, from this list, right? So this is just kind of creating an array of sets here. And then also, just to make life easier, we're going to make like a little lookup table with our words that will give us the index where they live in our matrix. And then here, this is kind of going to define our rows and columns like we saw earlier, right? Our rows are going to be for every word, and our columns will be for every document. And so with that, we create this little zero matrix right here, using these as the dimensions. And then because my NumPy is not like what it used to be, we're just going to make like a little bonus matrix for our IDF that will multiply our term frequency matrix by at the end. So basically what we're doing now is we just want to go through all of our documents, right? And for all of the words in the documents, we just want to count how many times they occur, right, which is happening here. And then we only want to count their presence in our like inverse document frequency matrix once, right? Because that matrix, it's just counting like a Boolean flag, right? Whether or not this word was present in a document or not, and we don't want to double count here because then that kind of defeats the purpose of the IDF matrix, the inverse document frequency matrix. So nothing really crazy. This is kind of just to demonstrate kind of how straightforward this algorithm is, but still like the cool results you can kind of get out of it. And then at the very end, we need to divide our term frequency matrix by the length of the words in that matrix, right? That kind of is the denominator we were talking about earlier. Basically with that, we have our term frequency matrix all finished. And then finally, we exit out of that for loop. We apply the kind of log scaling we mentioned earlier to our inverse document frequency matrix. Then we just multiply the two together, doing some funky NumPy matrix stuff that I had to Stack Overflow. And then we get our tf-idf map. So again, pretty straightforward, just kind of follows the algorithm we talked about before. We also output this unique words array, so that way we're able to understand what a given row in our matrix corresponds to. And then we get our document. So I'll just run through this quick example. It'll just show us data really similar to what we looked at before. So here's our three sentences, like we remember from the slides. And here are the outputs that are going to be created, and we're going to print them in a nice aesthetic way. And this is basically what we saw in our slides, just kind of reduced to decimals instead of the 3 logs. Any questions about this? We kind of went through it fast, but I feel like this is like the less interesting part of this. Is kind of just like code But any questions here? Otherwise, we'll just keep going and looking at some Spotify stuff. Cool, Spotify stuff. Again, here are words, here's the matrix. Here is us kind of doing the dot products to figure out, you know, the words as well. Today we're looking at the rows here. Yeah, and now we're going to do some like Spotify scraping and kind of talk about how we can use this data to build like these Spotify vectors. So I went ahead and kind of, the Spotify, I feel like working with any API is kind of like sucks. So I made like a little baby wrapper here. And yeah, this basically, you know, abstracts some common methods from the Spotify API for y'all. This is all in the GitHub that I linked, so you can look at that in your own time. But at a high level, just pull some data that we care about. So this is like a little Spotify scraper we made, and if we hit enter here, it'll authenticate for us. And so the problem that I'm going to try to use song vectors for today is kind of the idea of recreating albums based on what the people want the albums to be. So I'll call it like populist albums, right? And the idea is, you know, imagine a band has like, you know, 5 albums and like 10 songs on each album, but imagine some people only listen to like a subset of the songs on one and some listen to a subset on the other, right? It'd be kind of cool to redefine the albums based on like the listener trends, right? So that's kind of like the high level goal of this today. So to start, we need to pick an artist. I just picked Vampire Weekend for funsies. This is their Spotify artist ID. If you just go to Spotify and type in like Vampire Weekend and you copy their like link to share that Spotify URL, you can kind of just yank this from the URL and you get it. And so basically I wrote like a little helper function in the Spotify scraper. And we can actually just look at the helper function real quick, but it's pretty straightforward. It just hits this Spotify endpoint that they gave us in their docs. It just pulls out the unique albums and the songs on a given album, spits them out to us. So we're going to run that here. And this is our result. This is like really gross, right? These are the Spotify IDs, so it's kind of gibberish to us. But I also kind of logged a mapping of like the track ID to like a descriptive track name and the album ID to like an album name. So here, we kind of just do like this big kind of dictionary comprehension to make a little bit of a prettier output here. And so here like are some Vampire Weekend albums, or like all of their albums on Spotify at least, with all of the songs in the appropriate albums. That being said, like at the end of the day, we're probably going to want to use these really gross IDs, even though they're really gross, because we can kind of treat these as like individual words, right? Whereas these are like phrases, right? Or like a collection of words, so we can't treat them as individual words because they already have individual words in them, right? Whereas these are indeed like distinct words by nature because they're like Spotify IDs. Yeah, so with that in mind, now this is kind of the, I would say like the hardest part of this whole exercise because it's kind of involves like scraping and like creating data, right? So at a high level, what we want to do here is find all playlists that have like Vampire Weekend songs in them, and then once we get those, we can like, you know, do all the data analysis we want, but we have to get these playlists first, right? And so how do we do that? Here I have like this really shitty heuristic where I just picked some like Vampire Weekend buzzwords, right? And we're just going to query for like any playlist that has these buzzwords in them, right? Which is, you know, not 100% correct, because sometimes people name their playlists like funky stuff, right? And, you know, it might not be picked up here. And additionally, there's like a lot of playlists here, right? And we only have so much time to scrape stuff, and only like, you know, so much time until we get rate limited. And so, yeah, basically we're gonna get like a really like strong subset, and we might not get all the songs, right? You know, because if we look at like 200 random playlists, like what are the odds like White Sky, Basement Jaxx, Club Mix is gonna be in one of those 200 playlists, but it'll kind of give us some starting data. So I'm not going to run this again because I ran it earlier. This is like all the playlists I looked at. Every dot represents a playlist, and every plus represents when I found a playlist with at least 2 Vampire Weekend songs in them, because if we have like only one, it's kind of like a shitty vector, right? It's like, okay, we only have one song here, so we're going to make it its own vector, but that doesn't really make sense because what we care about is how two like songs or words that interact together to make your own vector. Yeah, so we scrape our songs, and then this is kind of the output of like all of the playlists with their song kind of cluster, not clusters, but like sets of songs from memory in a given playlist, right? So here you can see, you know, in the earlier example, we talked about like the and words like is and stuff like that as kind of like filler words. In this case, it seems like A-Punk and like Harmony Hall are kind of like filler songs in that like they're present in a lot of playlists, or maybe popular is a better word, present in a lot of playlists, but not necessarily distinct. So these are our results, prettified, so we don't see like the weird IDs, right? Here are our results, not prettified. And again, what we track here are like the Vampire Weekend tracks, and we also have to track like the total amount of songs in the playlist to get our denominator, right? Yeah, and now we have our playlist results, and now we can make a vector out of them. So we're gonna like do some really funky stuff to make the vector out of them, right? I mentioned earlier that you know, we're gonna treat these place IDs as words, right? And I want to recreate the TF-IDF algorithm we wrote earlier, because that works on like words and sentences. And I also don't want to like track all of the non-Vampire Weekend songs, because if I do, those will be new words in my TF-IDF matrix that I don't really care about, and those will also kind of sully my results. So to kind of get around this, we're gonna like turn every not Vampire Weekend song in the playlist into like a dummy word, which is going to be F. And so now we just have like a lot of Fs, and then like the Vampire Weekend songs, right? So these are kind of like our hacky conversion here. Any questions about like this part so far? We're basically just creating like sentences where the words are the track titles and the filler words are like the tracks that we don't care about. Anything I can clarify here? If not, we will keep going. Cool. Yeah, and so basically these are our funky like sentences that our machine is going to parse and understand. And so here is us kind of invoking the TF-IDF function from earlier, right? And so let's print out that and that works one at a time. Cool, so this is our big matrix that's like really poorly formatted. And here are our words, which are just our song titles. And I think earlier we defined kind of a lookup, so we can leverage that lookup. Do track tuning. So let's do track tuning word for word in AdWords. That'll be prettier. One second. Track tuning. What word? That's useful. Anyways, here is an example about why good data is really important to have. With that, I might segue into. I don't want to debug this. I'm not going to debug this. Okay, we'll talk about future applications. Yeah, what's up?
Yeah, so we have a question from people viewing on YouTube.
Yeah.
The question is, what kind of real-life applications does TF-IDF have, and what other data sets has this been used for?
Yeah, okay, so that's perfect. You should have asked that question like 30 seconds early, so I could have transitioned a little more smoothly. But I'll talk about some kind of applications. I was kind of brainstorming. I'm not sure, like, I know there are like real-world applications. I don't know like any like direct examples, but I think it's kind of been like eclipsed by more like advanced methods. Like Words Effect is like a really cool thing. You should check it out. And that I think is a lot more intelligent than what we're doing here. But like it's really good for like a hackathon, right? If you want to, you know, you have some kind of traditionally non-quantifiable data that you want to make quantifiable and like kind of discrete, right? You can use TF-IDF kind of just to get something started in a jiffy, right? So again, I think, you know, in the real world, like if you're at like some super big company, there's probably going to be some more modern, like deep learning, like techniques and stuff like that. But again, if you want to build like a really cool proof of concept at a hackathon, like I think it's like a really cool thing you can use to build it out. So I'm going to talk about some like random examples I kind of brainstormed when I was trying to legitimize this presentation. So we'll start with kind of a crowdsourced Spotify blend. So, you know, Spotify blend, just for context, is this pretty cool thing Spotify launched, where basically if you and a friend agree to make a blend together, it'll kind of create a playlist with like your shared taste. And at the end of the day, it's actually like not that intelligent. It's really just, you know, songs you listen to a lot, songs your friend listen to a lot, and just kind of clumps them together. And I'm sure the Spotify engineers will have like more to say about that, but that's to me what it looks like. But you can make something that's kind of like a crowdsourced Spotify blend, right? Based on kind of how people listen to these songs and playlists, right? So imagine we have a bunch of playlists, like a lot of playlists, like tens of thousands, right? And you take a random playlist of yours and a random playlist of your friends, right? And you turn them all into song vectors. What's really cool about vectors is we can like do all these mathematical operations on them, right? So you could take the average of your songs, of your playlist vector and your friend's playlist vector to get like an average playlist vector. And then you can kind of parse through like the global set of playlists in your data set and find the closest playlist, right? And that playlist would kind of represent mathematically what your friend's playlist and your playlist kind of together would make, right? So that's like a kind of a cool example of kind of a full like product you can build out of this pretty easily. And then I had some other kind of just random ideas that I didn't spend too much time thinking about, but one thing that could be kind of cool, right, is doing this analysis on like emoji groupings, right? So if you find like a bunch of tweets and you parse through all these tweets, you could kind of figure out semantically like emoji vectors, right? So like, you know, are like the monkey, like, you know, evil vectors, like are those like similar to each other quantifiably, or are they like, do they appear in different contexts, right? Stuff like that. So that's like kind of another cool idea. And then another thing you try to do is make like a Spotify like user matching software, right? So if you think people will be like good friends if they have good taste in music, right? Maybe you can treat users as documents, right? And treat the songs in all of their playlists as words, right? And so now you basically created like a user profile based on your listening history, right? And so you can then kind of like crawl through and see like, oh, like what Spotify listener is like most compatible with your taste, right? And stuff like that. So, and again, what's really cool is at the end of the day, I'm sure like y'all taking like some really cool like linear algebra classes and stuff like that, right? You can do all that like cool shit that you did in linear algebra on these vectors as well, right? And do any cool like, I don't know, maybe like, I'm not going to say any examples of that, my linear algebra is rusty, but there's like a lot of cool math you can apply here with these vectors, right? So that's really cool stuff. So, with that in mind, yeah, again, like we mentioned earlier, the hardest part of all of this was like getting like large amounts of data, right? Because if you only have like 2-3 sentences, right, like the dog sentences, that's kind of like, you're not going to gain any like big semantic introspections about like what dog means with those 3 sentences, right? But if you have like millions and millions of sentences, and you can kind of compare those millions of sentences together, you're going to get like a lot more kind of robust and like intertwined, but like yet unintertwined through this algorithm information about your data. So yeah, getting lots of data is hard, but really important for ML models. And with that, we will talk about a word from our sponsors, which is scale. We do a lot of stuff with data. At the end of the day, we have like these ML companies all over, right? Some of them like self-driving cars. Some of them build like what would you do if not build a self-driving car? But like you know, other things that are equally important. I'll have the examples that are not like specific, but yeah, at the end of the day, these customers really rely on like a high volume of like really well labeled data, and that's kind of what Scale provides. So Scale is hiring. We are hiring for new grads or interns for software engineers, new grads or interns for ML research engineers, or if you want to be more like a non-technical but still kind of technical product ops manager, we're looking for new grads there as well. and job postings are on the DL. So you can talk to us either tomorrow at our booth, or via Slack, or by emailing us, any one of us on these emails. Cool place, lots of really interesting problems. Oh, there's a question like, does Scale use stuff like TF-IDF? I think we do kind of like a bunch of crazy stuff depending on the problem, and there's like a little bit of kind of researchiness, because all our customers are like all different, right? And they're all trying state-of-the-art stuff, and we all need to collect data for them in like novel ways, right? So for like given customers when we're like working with them and figuring out how to label their data better, we kind of do a lot of kind of research and experimentation, and kind of like sniffing out cool techniques for, again, like pulling out data that just depends on the day. So, oh yeah, question?
Yeah, there's another one. Does Scale have any APIs or packages that hackers can use for their projects over this weekend?
Not really. So I think the closest thing that we have, which I don't think would be like, yeah, I don't think like anything that's like free. But like the closest thing we have is called Scale Rapid, and that's a pretty cool offering, which is like if you want like kind of a ad hoc data set labeled, you can kind of be like, oh, like here's like some data, here's kind of the high level instructions, like can you label it for me accordingly, and we like give you the data back. But I don't think we have anything great for the hacker specifically. Yeah, but that's a good question. We have a great swag for hackers, that's useful, and we also have great job opportunities for hackers, and we also have a cool challenge tomorrow at our booth. It'll be like kind of a coding puzzle with prizes on the line, but yeah, no technical offerings for hackers. Yeah, were there any other questions?
Nothing really relevant.
Okay, cool. YouTube. Okay, cool. Yeah, that's basically all I've got. If anyone has like questions about the slides, feel free to ask them now. If anyone has questions about Scale, we'll probably, me and some other excellent Scale folks will be sticking around after, and y'all can chat us up, give us resumes, stuff like that. But yeah, that's all I've got. No questions? Oh,
Matt,
yes.
I have a question.
What's your question?
Could you tell us a little bit about more like what you do at Scale?
Oh, what do I do? Yeah.
Tell us what your experience working at
Kind of
Scale.
important, yeah. Okay, so yeah, I work on our 3D team, which we work a lot with like self-driving car companies. I'm trying to think of like the ones like, we work like with self-driving car companies, and basically I do a lot of cool stuff around like making point clouds like labelable, which like sounds easy, but it's not as easy as you might think, because at the end of the day, you have like these really high-tech companies like taking like millions of points at a given like tenth of a second, right? And I need to load that over like several seconds on a computer and label these like millions of points. So there's like a lot of really cool kind of computational problems. All those like algorithm classes, you're like, this is like 4 and why all I need is 8. Like that stuff comes in handy a lot at Scale too, which is really cool. So stay in school. And yeah, a lot of kind of like room to apply like cool mathematical stuff, but also a lot of like open-ended problem solving. Another kind of really interesting part of Scale is, we manage this workforce which labels our data, and so you also have this kind of aspect of like game theory and like how do we like incentivize people properly, right? The analogy I really like is Scale is like Uber if nobody knew how to drive, right? Because Uber, at the end of the day, they're like maintaining this workforce of drivers, but they know how to do their job, right? And we're maintaining this workforce of labelers, but they don't know how to label the data because the customer like comes with different ways you want to label data, like new state-of-the-art stuff, and we have to kind of keep these people trained. So there's a lot of kind of technical challenges, but also a lot of operational challenges. So depending on what you're interested in, there's definitely stuff for you here. Yeah, I've been here for about 2 years. I started as a new grad back in the day, and yeah, definitely learned a lot of crazy stuff, both technically and like introspectively. And yeah, it's been a cool experience for sure. And yeah, definitely feel free to A, just ask us any more questions about Scale if you have them, or B, hit us up to apply for our offerings. Yeah.
Do you guys have a preference which email people reach out to? Like, would it be Sophia?
Mine is Matthew, so let that speak for itself. But I don't think we have a preference. Sophia's like in charge of like a lot of recruiting stuff, so she's also a good person. Also, Jessica and Will are also great people. Also, Brian is, even though he's not here, super
Just
awesome
email
person.
me, Sophia@scale.com.
But she's less diplomatic than me, I guess. So yeah, she's a good person to email as well. Yeah. Cool. happy Friday, happy hacking. Hit up our booth tomorrow. Cool puzzle, cool prizes. Yeah, thanks for coming, y'all.